4.5 billion years ago, our planet takes its first breath. Picture Earth in its infancy, a molten hellscape where the surface glows cherry red and temperatures soar above 2000 degrees Fahrenheit. The ground beneath is not solid rock but a churning ocean of liquid stone. And then, something extraordinary happens. The planet exhales. Volcanic gases burst from countless fissures in the molten crust, releasing water vapor, carbon dioxide, methane, and ammonia into the void above. These aren't gentle puffs of steam, they're violent explosions that hurl gases miles into space. But here's what's really happening. Earth is creating its first atmosphere, one volcanic breath at a time. The early atmosphere bears no resemblance to the air we breathe today. If you could somehow survive the heat and stand on that primordial surface, you'd suffocate instantly. No oxygen exists yet. Instead, the air consists almost entirely of water vapor and carbon dioxide, with traces of methane and ammonia swirling in the mix. The atmospheric pressure crushes down at nearly 100 times what we experience today. Imagine diving 3,000 feet underwater, and you'd feel similar pressure, but something remarkable begins to unfold. As millions of years pass, the planet starts to cool. The water vapor in the atmosphere condenses into droplets, then streams, then torrential rains that last for millennia. These aren't ordinary storms, they're planetary deluges that create the first oceans while simultaneously thinning the atmosphere. The pressure drops, the temperature falls, and Earth's atmosphere begins its long journey toward becoming the life-sustaining envelope we know today. Here's the mind-bending part. The air you're breathing right now contains atoms that were exhaled by those ancient volcanoes. Every breath connects you directly to Earth's violent birth. The nitrogen that makes up 78% of our atmosphere has been cycling through the planet's systems for billions of years, while the oxygen we depend on wouldn't appear for another 2 billion years, created by the first photosynthetic organisms that learned to harness sunlight. Fast forward through deep time to when humans first gaze upward and wonder about the sky above their heads. Picture a Mesopotamian village 5,000 years ago. The sun sets behind distant mountains, and wisps of clouds drift across the deepening sky. But these aren't just random formations to the people below, they're messages written in a celestial language that shamans and priests have learned to read like sacred texts. The earliest weather watchers discover something profound. The sky has patterns. Certain cloud formations arrive before storms. Winds shift direction before seasons change. The position of stars correlates with flooding rivers and drought-stricken fields. These ancient observers don't understand the physics behind what they're seeing, but they recognize something fundamental. The atmosphere operates according to rules that can be observed, recorded, and even predicted. In ancient Egypt, priests along the Nile River develop a sophisticated understanding of their local weather patterns. They notice that the river floods predictably each year, usually beginning in late June and reaching peak levels by September. But here's what makes their observations remarkable. They connect these floods to weather patterns occurring hundreds of miles upstream in regions they've never seen. The Egyptian flood predictions become so accurate that they can forecast harvest yields years in advance. They're reading the atmosphere's signals with mathematical precision, tracking how seasonal wind patterns in Central Africa create monsoon rains that swell the Nile's tributaries. Without understanding evaporation, condensation, or atmospheric circulation, they're essentially creating the world's first long-range weather forecasts. Meanwhile, in ancient Greece, philosophers begin asking different questions about the sky above. Instead of simply observing patterns, they want to understand why those patterns exist. Aristotle, writing around 350 years before the Common Era, documents the first systematic observations of wind patterns, rainfall cycles, and storm behavior. Here's what Aristotle notices. Winds have preferred directions that change with the seasons. Storms often approach from specific compass bearings. Rainfall varies not just from year to year, but according to geographic location. Mountains receive more precipitation than valleys. Coastal areas experience different weather than inland regions. He's identifying the fundamental truth that weather is driven by geography, season, and the sun's changing position in the sky. But Aristotle makes an even more remarkable discovery. He observes that people struggle to breathe at high altitudes, particularly when climbing mountains. Without understanding atmospheric pressure or the physics of gases, he deduces something extraordinary. Air has weight. The higher you climb, the less air exists above you, making breathing more difficult. This insight represents a pivotal moment in human understanding. For the first time, someone recognizes that the atmosphere isn't an infinite expanse of nothingness. It's a finite envelope surrounding the planet, with measurable properties that change with altitude. Air, which seems weightless when you wave your hand through it, actually presses down on everything at sea level with a force of nearly 15 pounds per square inch. Think about what this means. The air above your head right now weighs approximately 2,000 pounds per square foot, the equivalent of a small car pressing down on every square foot of surface area. You don't feel this crushing weight because the air inside your lungs pushes outward with equal pressure, creating perfect balance. But climb a mountain or ascend in an airplane, and the body immediately notices the pressure difference as the weight of air above you decreases. These early observations set the stage for humanity's greatest atmospheric adventure. Ancient weather watchers established several fundamental principles that still guide meteorology today. The atmosphere has patterns that can be observed and predicted. Weather varies systematically with geography and season, and air itself has physical properties that can be measured and studied. But perhaps most importantly, these early observers recognized that understanding weather requires looking at the sky not as a distant, unknowable realm, but as an extension of the Earth itself, a dynamic system that connects mountains to valleys, oceans to deserts, and local weather patterns to global atmospheric circulation. The shamans reading cloud formations, the Egyptian priests predicting Nile floods, and Greek philosophers documenting wind patterns are all participating in the same fundamental human endeavor, learning to read the language of the atmosphere. They're discovering that the seemingly chaotic dance of clouds, winds, and storms actually follows rules that can be understood through careful observation and logical thinking. Here's what's truly remarkable about these ancient achievements. Using only their naked eyes and basic measuring tools, early weather watchers identify atmospheric phenomena that modern meteorologists study with satellites, radar, and supercomputers. They recognize seasonal wind patterns that we now know are driven by the planet's tilt and rotation. They predict flooding based on distant weather conditions, demonstrating an intuitive understanding of how atmospheric systems connect across vast distances. The foundation they establish that weather can be observed, understood, and predicted becomes the launching point for every subsequent breakthrough in atmospheric science. From these humble beginnings, watching clouds and feeling the wind, humanity embarks on a journey that will eventually take us into the heart of hurricanes, to the edge of space, and deep into the mathematical equations that govern how our atmosphere works. The ancient weather watchers couldn't have imagined that their careful observations of cloud patterns and seasonal winds would eventually lead to satellite images of entire hurricane systems, computer models that predict weather a week in advance, or the discovery that Earth's atmosphere is just one example of planetary atmospheres throughout the universe. But their fundamental insight that the sky above operates according to discoverable patterns opens the door to understanding one of the most complex and beautiful systems on our planet. As we stand on their shoulders and look upward at the same sky that captivated ancient observers, we see not just clouds and blue expanse, but a three-dimensional ocean of moving air that connects every place on Earth. The atmosphere that began with volcanic gases 4.5 billion years ago has become the stage for an ongoing dance of energy, water, and wind that creates the weather patterns sustaining all life on our planet. The story of weather is really the story of how humans learned to read the sky and, in doing so, discovered that we live within one of the universe's most intricate and essential systems. Every breath we take, every cloud we observe, every storm we experience connects us to that ancient moment when Earth first exhaled and began creating the atmosphere that makes our existence possible. The adventure into understanding weather has only just begun. The year is 1643, and Evangelista Torricelli is about to accidentally revolutionize our understanding of the invisible ocean above our heads. Torricelli, a student of Galileo, faces a practical problem that well diggers have struggled with for centuries. No matter how powerful their pumps, they cannot draw water from wells deeper than 34 feet. The conventional wisdom blames this limitation on nature's supposed horror of vacuum, the ancient belief that nature abhors empty space so much that it will only allow water to rise so high before refusing to cooperate further. But Torricelli suspects something else is at work. He fills a glass tube, 4 feet long and sealed at one end, completely with mercury. Then, in a moment that will change science forever, he inverts the tube and places the open end into a dish of mercury. Here's what happens next. The mercury in the tube drops, but not all the way. It settles at exactly 30 inches above the mercury in the dish, leaving an empty space at the top of the tube. That empty space shouldn't exist according to the conventional wisdom. Nature should be horrified by that vacuum and force the mercury to fill the entire tube. But the mercury sits stubbornly at 30 inches, no matter how Torricelli adjusts the apparatus. He's created something that will become known as the first barometer, and in doing so, he's proven something extraordinary. Air has weight. Here's what's really happening in that glass tube. The atmosphere above us all the way up to the edge of space presses down on the mercury in the dish with a force of 14 7/10 pounds per square inch. This invisible pressure pushes mercury up into the tube until the weight of the mercury column exactly balances the atmospheric pressure pressing down. At sea level, this balance occurs when the mercury rises precisely 30 inches, or 760 millimeters. The implications stagger the scientific community. The atmosphere isn't weightless ether. It's a massive ocean of air that presses down on everything at Earth's surface with tremendous force. Every square inch of your body right now experiences the equivalent weight of a 14-pound bowling ball pressing against it. You don't feel crushed because the air inside your lungs, your bloodstream, and even the spaces between your red face cells pushes outward with exactly the same pressure. Think about this remarkable balance. Your body exists in a state of perfect equilibrium between the crushing weight of the entire atmosphere and the internal pressure of gases dissolved in your blood and tissues. When that balance shifts, when you dive underwater or climb a mountain, your body immediately responds with popping ears, changing breathing patterns, and other adjustments to maintain equilibrium. Torricelli's mercury column becomes the first tool capable of measuring invisible atmospheric changes. When the mercury rises above 30 inches, it indicates high atmospheric pressure, usually associated with clear, stable weather. When it drops below 30 inches, low pressure approaches, often bringing storms, clouds, and unsettled conditions. For the first time in human history, people can literally see the weight of the sky changing from day to day. But Torricelli's discovery raises an immediate question. If air has weight, and if that weight decreases with altitude as Aristotle observed, exactly how does atmospheric pressure change as you climb higher? Enter Blaise Pascal, the brilliant French mathematician and physicist who decides to test this question with scientific precision. In 1648, Pascal carries a mercury barometer up Puy de Dôme, a dormant volcano in central France that rises nearly 5,000 feet above sea level. This isn't a casual afternoon hike. It's a carefully planned scientific expedition designed to measure how atmospheric pressure changes with altitude. Pascal's brother-in-law, Florent Perrier, leads the actual climb, while Pascal coordinates measurements from multiple locations. As the expedition ascends the mountain, something remarkable happens. The mercury in the barometer drops steadily and predictably. At the base of the mountain, it sits at 30 inches, just as Torricelli's experiments predicted. But with each 1,000 feet of elevation gained, the mercury drops approximately 1 inch. At the summit, the mercury reads only 27 inches, 3 inches lower than at sea level. Here's what this means. Every 1,000 feet you climb removes about 10% of the atmospheric pressure pressing down on you. The air doesn't just get thinner. Gradually, it decreases exponentially. At 18,000 feet, the altitude of Mount McKinley, atmospheric pressure drops to half of sea level values. At the cruising altitude of commercial aircraft around 35,000 feet, atmospheric pressure plummets to less than 1/4 of what we experience at sea level. Pascal's mountain experiment establishes the fundamental relationship between altitude and atmospheric pressure that still guides aviation, mountaineering, and weather prediction today. But more importantly, it proves that Earth's atmosphere has a measurable structure. The air above us isn't uniform, it's layered, with each layer having different density, pressure, and temperature characteristics. This discovery inspires a new generation of atmospheric explorers who want to venture higher than any mountain can take them. Enter the age of ballooning, when daredevil scientists risk their lives to explore the vertical frontier of Earth's atmosphere. Jacques Charles, inventor of the hydrogen balloon, makes the first scientific ascent in 1783. Rising to nearly 9,000 feet above Paris, he measures temperature drops of 35 degrees Fahrenheit from ground level to his maximum altitude. But Charles is just the beginning. Other balloonists push higher, into regions where the cold becomes brutal and breathing becomes desperately difficult. Joseph Gay-Lussac, the French chemist, makes perhaps the most daring ascent of the early balloon era. In 1804, he rises to an astounding 23,000 feet above sea level, higher than all but the tallest mountains on Earth. At this altitude, the temperature plunges to -9 degrees Fahrenheit, and the atmospheric pressure drops to less than 1/3 of sea level values. Gay-Lussac can barely breathe, and his instruments nearly freeze, but he successfully measures temperature, pressure, and humidity at altitudes no human had ever reached. Here's what these balloon pioneers discover. The atmosphere has a remarkably consistent structure. Temperature drops steadily as you ascend, decreasing approximately 3.5 degrees Fahrenheit for every 1,000 feet of altitude gained. This rate of cooling, known as the environmental lapse rate, occurs because air expands and cools as atmospheric pressure decreases with height. But the balloonists make an even more important discovery about atmospheric circulation. From their lofty perches, they observe that winds at different altitudes often blow in completely different directions from surface winds. They're seeing the first evidence of the layered wind patterns that we now know control global weather systems. At ground level, you might experience a gentle breeze from the east, but 5,000 feet above your head, winds might rage from the west at 40 miles per hour. 10,000 feet higher still, the wind direction might shift again, with speeds reaching 60 or 70 miles per hour. These early aerial observers are mapping the three-dimensional structure of atmospheric circulation for the first time. The balloon expeditions reveal that Earth's atmosphere operates like a vast machine with multiple moving parts. Surface heating by the sun creates pressure differences that drive winds horizontally across the planet's surface. But simultaneously, warm air rises and cold air sinks, creating vertical circulation patterns that transport heat, moisture, and momentum between different atmospheric layers. Here's the remarkable thing about these vertical air movements. They're constantly redistributing energy from Earth's surface to the upper atmosphere and back. Again, warm air rising from sun-heated ground carries water vapor upward, where it condenses into clouds and releases latent heat. This process powers thunderstorms, drives hurricane formation, and creates the precipitation that sustains all terrestrial life. The pressure measurements taken by Torricelli, Pascal, and the early balloonists established the foundation for understanding weather as a three-dimensional phenomenon. Weather doesn't just happen at ground level. It's the result of complex interactions between atmospheric layers, extending from Earth's surface to the edge of space. Every storm system, every front passage, every change in local weather reflects pressure differences and air movements occurring throughout the entire vertical column of atmosphere above your head. When meteorologists today analyze weather patterns, they're examining atmospheric pressure, temperature, and wind data from the surface up to 50,000 feet or higher. Building on the discoveries made by those early atmospheric pioneers, the barometer sitting on your wall or weather app on your phone traces its lineage directly back to Torricelli's glass tube filled with mercury. Every pressure reading represents the weight of the entire atmosphere pressing down, just as those first mercury columns revealed 3.5 centuries ago. The numbers might be displayed digitally now, but the fundamental principle remains unchanged. Atmospheric pressure tells the story of invisible air movements that create the weather we experience. As we breathe the air around us, we're existing at the bottom of an atmospheric ocean that extends 60 miles above our heads. Every breath draws in air molecules that have traveled vast distances, riding circulation patterns mapped by balloon explorers who risked their lives to measure the invisible architecture of our sky. The atmosphere that once seemed like empty space above our heads reveals itself as a dynamic, structured, measurable system, whose properties change predictably with altitude and time. The secrets that pressure revealed in those early experiments continue to guide weather prediction, aviation safety, and our understanding of climate systems around the world. From Torricelli's mercury tube to space-age satellite measurements, we're still essentially weighing the sky, measuring the invisible forces that drive weather across our planet. The storm approaches Philadelphia on a humid afternoon in June 1752, and Benjamin Franklin prepares to risk his life for science. Franklin has been thinking about lightning for years, developing a theory that seems almost absurd to his contemporaries. He believes lightning is nothing more than electrical discharge, similar to the sparks generated by rubbing silk against glass in laboratory experiments. If he's correct, then thunderstorms are essentially massive electrical generators, and lightning bolts are nature's way of releasing accumulated electrical charge. But proving this theory requires getting close enough to lightning to study it directly, a proposition that has already killed several European experimenters who attempted similar investigations. Franklin's plan involves flying a kite during a thunderstorm, with a metal key tied to the silk string near his hand. If lightning strikes the kite, electrical current should flow down the wet string to the key, proving that lightning and laboratory electricity are the same phenomenon. As the storm intensifies, Franklin launches his kite into the turbulent air. Dark clouds boil overhead, and rain begins to soak the silk string, making it increasingly conductive. Then it happens, a flash of lightning illuminates the sky, and immediately afterward, Franklin feels the hair on his arm stand up. The metal key begins to spark, sending tiny electrical discharges into the surrounding air. Here's what's actually happening. The thunderstorm above Franklin's head contains electrical charges, separated by powerful updrafts and downdrafts within the cloud. Ice crystals and water droplets collide millions of times per second, stripping electrons from some particles and adding them to others. This process creates vast electrical potential differences, sometimes exceeding 100 million volts between the ground and the storm cloud. When Franklin's kite enters this electrically charged environment, it becomes a conductor that allows some of the storm's electrical energy to flow harmlessly to ground through the wet string. The sparks jumping from the key represent the same electrical force that creates lightning bolts, but in much smaller quantities. Franklin has successfully captured and channeled the power of the storm, proving that lightning is indeed electrical in nature. This experiment revolutionizes our understanding of thunderstorms. Lightning isn't the anger of gods or supernatural phenomenon. It's the result of measurable physical processes occurring within storm clouds. Each lightning bolt releases approximately 1 billion to 5 billion joules of energy in a discharge lasting less than 1 millisecond. To put that in perspective, a single lightning strike contains enough energy to power a typical household for several weeks. But Franklin's electrical discoveries lead to an even more important innovation: the lightning rod. By mounting pointed metal conductors on building rooftops and connecting them to underground cables, Franklin creates a system that safely channels lightning's electrical energy into the earth rather than allowing it to start fires or damage structures. This simple device saves countless lives and property throughout the world, demonstrating how understanding natural phenomena can lead to practical protection against their destructive power. While Franklin investigates the electrical nature of storms, another maritime pioneer focuses on understanding wind patterns and storm intensity. Admiral Francis Beaufort of the British Royal Navy spends decades battling Atlantic gales and hurricanes, developing an intimate knowledge of how wind speed relates to sea conditions and weather patterns. Beaufort recognizes that accurate wind measurement is crucial for safe navigation, but existing methods prove inadequate for shipboard use. Mechanical wind instruments work poorly on moving vessels, and subjective descriptions like strong breeze or heavy gale mean different things to different sailors. The British Navy needs a standardized system for describing wind conditions that produces consistent results, regardless of who makes the observation. In 1805, Beaufort creates his famous wind scale, correlating observable effects with specific wind speed ranges. His system starts with force 0, complete calm, where smoke rises vertically and sea surfaces appear mirror smooth. Force 1 describes light air at 1 to 3 miles per hour, where smoke drifts but leaves and flags barely move. The scale progresses through gentle breezes, moderate winds, and fresh gales up to force 12 hurricane conditions with winds exceeding 74 miles per hour, where waves exceed 45 feet in height, and visibility drops to near zero in driving spray. Here's what makes Beaufort's scale revolutionary. It transforms subjective wind observations into objective measurements based on universally observable effects. A sailor anywhere in the world can look at wave conditions, flag movements, or tree behavior and assign an accurate Beaufort number that corresponds to specific wind speeds. This standardization allows weather observers to communicate wind conditions precisely across vast distances and different languages. The Beaufort scale remains in use today, nearly 200 years after its creation, because it captures something fundamental about how wind speed affects the visible world around us. Meteorologists still use Beaufort numbers to describe wind conditions, and the scale provides an intuitive way for non-scientists to understand storm intensity. When weather forecasters mention gale-force winds or hurricane conditions, they're using categories that trace directly back to Beaufort's careful observations of wind effects on ships and sea conditions. But the most transformative development in early weather science isn't a single discovery. It's the invention of the telegraph, which revolutionizes weather prediction by enabling real-time communication across continental distances. Before the telegraph, weather observers work in isolation. A meteorologist in Chicago might measure dropping barometric pressure and rising winds, but has no way to know whether similar conditions exist in cities hundreds of miles away. Weather systems move across the landscape faster than information can travel by horseback or ship, making it impossible to track storms or predict their arrival at distant locations. The telegraph changes everything. By 1850, telegraph lines connect major cities from Boston to Chicago, allowing weather observers to transmit barometric readings, temperature data, and storm reports in real time. For the first time in human history, meteorologists can see weather patterns developing across entire continents. Joseph Henry, the first secretary of the Smithsonian Institution, recognizes the revolutionary potential of telegraphic weather reporting. In 1849, he establishes a network of volunteer weather observers throughout the United States, equipped with standardized instruments and instructions for taking simultaneous measurements. Each day at the same time, observers from Minnesota to Florida transmit their data to Washington, where Henry's staff plots the information on large maps. The results astound everyone involved. Weather patterns that seemed random and unpredictable when viewed from individual locations reveal themselves as organized systems moving across the continent in recognizable patterns. Storm centers can be tracked as they move from the Great Plains toward the Atlantic coast. Temperature fronts become visible as organized boundaries separating different air masses. The chaotic local phenomenon of weather transforms into an understandable continental scale system. Here's what the telegraph network reveals about storm systems. They move predominantly from west to east across North America, typically traveling at speeds between 20 and 40 miles per hour. Low-pressure systems, identified by below-normal barometric readings, almost always bring unsettled weather, including clouds, precipitation, and strong winds. High-pressure systems produce the opposite effects: clear skies, light winds, and stable conditions. But most importantly, the telegraph observations reveal that storms have predictable structure. Low-pressure systems rotate counterclockwise in the northern hemisphere, with winds spiraling inward toward the center. This rotation creates organized weather patterns around storm centers, with specific types of clouds, precipitation, and wind conditions occurring in predictable locations relative to the storm center. The Smithsonian Weather Network represents the first systematic, real-time weather monitoring system in human history. Henry's observers take measurements using identical instruments at exactly the same times each day, creating a standardized dataset that reveals continental weather patterns with unprecedented clarity. The daily weather maps produced from telegraph reports become the foundation for modern weather forecasting, demonstrating that storms can be tracked and predicted hours or even days before they arrive at specific locations. By 1860, the telegraph network includes over 500 volunteer observers spread across the United States. Each morning, their combined reports create a snapshot of weather conditions from coast to coast, revealing the locations, movements, and intensities of storm systems affecting the continent. Weather prediction evolves from folklore and local observation to scientific analysis based on comprehensive, real-time data. The collaboration between Franklin's electrical discoveries, Beaufort's wind measurements, and Henry's telegraph network establishes the scientific foundation for modern meteorology. Lightning reveals itself as a measurable electrical phenomenon rather than supernatural force. Wind speeds become quantifiable through standardized observation methods, and storm systems transform from unpredictable local events to trackable continental-scale phenomena that follow discoverable patterns. These breakthrough discoveries demonstrate something profound about the atmosphere. It operates according to physical laws that can be understood, measured, and used to predict future conditions. The seemingly chaotic dance of storms, winds, and weather reveals itself as an organized system governed by pressure differences, electrical processes, and circulation patterns that extend across vast distances and timescales. From Franklin's kite experiment to Henry's telegraph network, each discovery builds upon previous knowledge while revealing new layers of atmospheric complexity. The electrical nature of storms, the standardization of wind measurement, and the real-time tracking of weather systems combined to create the first truly scientific approach to understanding and predicting weather patterns across continental distances. 29,000 feet above the Pacific Ocean, a formation of American B-29 bombers encounters something that shouldn't exist. The year is 1944, and these aircraft are flying toward Japan on what should be a routine bombing mission. The pilots have planned their route carefully, calculating fuel consumption and flight times based on expected wind conditions. But as they reach their cruising altitude, something extraordinary happens. Their ground speed increases by nearly 200 miles per hour, even though their airspeed remains constant. The pilots have stumbled into a river of wind racing through the upper atmosphere at velocities that seem impossible. This invisible aerial highway stretches thousands of miles across the Pacific, flowing from west to east at speeds exceeding 200 miles per hour. The bomber crews don't realize it yet, but they've discovered the jet stream, a phenomenon that will revolutionize our understanding of global weather patterns and atmospheric circulation. Here's what's actually happening at that altitude. The dramatic temperature difference between polar and tropical air masses creates enormous pressure gradients in the upper atmosphere. Cold air over the Arctic contains much less energy than warm air over the equator, and this temperature contrast intensifies with altitude. Around 30,000 feet above sea level, these pressure differences become so extreme that they accelerate air movement into narrow, fast-moving rivers of wind that circle the globe. The jet stream isn't a single wind current. It's actually multiple streams that meander across the planet like atmospheric rivers. The polar jet stream, which the B-29 pilots encountered, typically flows between 30 and 40,000 feet altitude, marking the boundary between cold polar air and warmer temperate air masses. A second river, the subtropical jet stream, flows at similar altitudes but farther south, separating tropical air from temperate regions. These aerial highways don't flow in straight lines. They undulate north and south in massive waves called Rossby waves, creating patterns that extend thousands of miles across continents. When the jet stream dips southward, it carries cold Arctic air into normally temperate regions. When it bulges northward, warm tropical air penetrates far into polar latitudes. These meandering patterns control much of the weather we experience at ground level. Think about the scale of energy involved in these atmospheric rivers. The polar jet stream alone transports approximately 100 times more water vapor than the Amazon River carries liquid water. The kinetic energy contained in jet stream winds exceeds the total electrical power generation capacity of the entire United States. These aren't gentle breezes, they're massive conveyor belts of energy that redistribute heat, moisture, and momentum around the planet. But the discovery of high-altitude wind patterns represents just one breakthrough emerging from World War II aviation technology. Simultaneously, radar operators tracking aircraft make an accidental discovery that revolutionizes our ability to see inside storms. Radar systems designed to detect enemy aircraft begin picking up mysterious echoes that don't correspond to any known targets. These ghost signals appear and disappear unpredictably, often covering vast areas and moving in patterns that seem unrelated to aircraft activity. Initially, operators dismiss these returns as equipment malfunctions or enemy jamming attempts. Then someone makes the connection. The mysterious radar echoes correspond exactly with areas of precipitation. Rain droplets, ice crystals, and snowflakes reflect radio waves back to radar receivers, creating images of storm structure that are completely invisible to the naked eye. For the first time in human history, we can see inside clouds and observe the internal architecture of weather systems. Early weather radar reveals astonishing details about storm organization. Instead of chaotic masses of clouds and precipitation, storms display intricate internal structure with organized patterns of updrafts, downdrafts, and rotation. Thunderstorms appear as towering columns of reflected energy, with clear boundaries between areas of heavy precipitation and surrounding clear air. But the most dramatic radar discoveries involve severe thunderstorms and tornado formation. Doppler radar, which measures the motion of raindrops and ice crystals within storms, reveals something extraordinary. Some thunderstorms contain rotating updrafts called mesocyclones that extend from near ground level to altitudes exceeding 50,000 feet. These rotating columns of air, 10 to 20 miles in diameter, create the conditions necessary for tornado formation. Here's what radar shows us about tornado development. The process begins with wind shear differences in wind speed and direction at various altitudes that cause horizontal rotation in the lower atmosphere. When a strong thunderstorm updraft encounters this rotating air, it tilts the rotation vertical, creating a mesocyclone. If conditions align perfectly, a narrow funnel of intensely rotating air extends downward from the mesocyclone, eventually reaching the ground as a tornado. Radar measurements reveal that tornado wind speeds can exceed 300 miles per hour velocities that were previously thought impossible in Earth's atmosphere. The strongest tornadoes contain wind speeds comparable to those found in Category 5 hurricanes, but concentrated into areas only a few hundred yards wide. These rotating storms create some of the most extreme weather conditions on our planet, with pressure drops so rapid that buildings literally explode outward as the tornado passes overhead. While radar technology opens windows into storm structure, another group of atmospheric explorers pushes the boundaries of altitude exploration beyond anything attempted before. The German V2 rocket program, originally designed as a weapon, becomes an unexpected tool for atmospheric research when captured rockets are repurposed for scientific missions. Starting in 1946, V2 rockets launched from White Sands Missile Range in New Mexico carry scientific instruments to altitudes exceeding 100 miles above Earth's surface. These vertical expeditions penetrate layers of atmosphere that no balloon or aircraft can reach, transmitting data about temperature, pressure, and atmospheric composition from the edge of space. The rocket measurements reveal that Earth's atmosphere has a much more complex vertical structure than anyone imagined. Temperature doesn't simply decrease with altitude. As balloon flights suggested, it follows a complex pattern of warming and cooling that defines distinct atmospheric layers with dramatically different properties. In the troposphere, extending from ground level to approximately 6 miles altitude, temperature decreases steadily with height, dropping about 3.5 degrees Fahrenheit per 1,000 feet of elevation. This layer contains virtually all weather phenomena, from ground-level fog to the tops of the highest thunderstorms. But above the troposphere lies the stratosphere, where something remarkable happens. Temperature stops decreasing and begins to increase with altitude. Between 6 and 30 miles above sea level, atmospheric temperature rises from minus 80 degrees Fahrenheit to nearly freezing. This temperature inversion creates an extremely stable atmospheric layer that acts like a lid, preventing most weather disturbances from penetrating higher into the atmosphere. Here's what causes the stratospheric temperature increase: ozone. At altitudes between 10 and 25 miles above sea level, oxygen molecules absorb ultraviolet radiation from the sun and split into individual oxygen atoms. These atoms recombine with other oxygen molecules to form ozone, releasing heat in the process. The ozone layer essentially functions as Earth's solar shield, absorbing dangerous ultraviolet radiation while heating the stratosphere through photochemical reactions. The rocket flights reveal even higher atmospheric layers with increasingly exotic properties. Above the stratosphere lies the mesosphere, where temperatures plummet to minus 130 degrees Fahrenheit, the coldest temperatures anywhere in Earth's atmosphere. Higher still, in the thermosphere beginning around 50 miles altitude, solar radiation heats the sparse atmosphere to temperatures exceeding 1,000 degrees Fahrenheit. Though the air density is so low that a thermometer would actually read freezing, these vertical expeditions demonstrate that Earth's atmosphere extends far beyond the breathable air near the surface. The atmosphere gradually transitions from dense, weather-producing air at ground level to the vacuum of space at altitudes exceeding 400 miles. Each layer has unique characteristics that influence weather patterns, radio communications, and even the survival of satellites orbiting Earth. The discovery of atmospheric layers explains many previously mysterious phenomena. The jet streams flow at the boundary between the troposphere and stratosphere, where temperature changes create the pressure gradients that accelerate high-altitude winds. Most commercial aircraft cruise in the lower stratosphere, taking advantage of jet stream tailwinds while avoiding the turbulence and weather disturbances confined to the troposphere below. The ozone layer's location in the stratosphere protects all life on Earth's surface from lethal ultraviolet radiation. Without this thin shield of gas molecules 20 miles above our heads, solar radiation would sterilize the planet's surface, making complex life impossible. The ozone layer represents one of Earth's most critical atmospheric features, even though it's completely invisible and imperceptible from ground level. Understanding atmospheric structure also explains why weather occurs only in the troposphere. The temperature inversion at the tropopause, the boundary between troposphere and stratosphere, creates a ceiling that prevents most air currents from penetrating higher into the atmosphere. Thunderstorms that attempt to grow beyond this boundary encounter increasingly warm air above them, which stops their upward development and spreads their tops into the characteristic anvil shapes visible from below. From the accidental discovery of jet streams by World War II pilots to rocket measurements of atmospheric layers, this era of exploration reveals the three-dimensional architecture of Earth's atmosphere. Weather isn't just a surface phenomenon. It's the result of complex interactions between atmospheric layers extending from ground level to the edge of space. The invisible highways of the jet streams, the rotating structure revealed by radar, and the layered atmosphere mapped by rockets combine to show us that weather systems operate within a precisely organized vertical environment. Every storm, every front passage, every change in local weather reflects processes occurring throughout the entire atmospheric column above our heads. These discoveries establish the foundation for modern meteorology, demonstrating that accurate weather prediction requires understanding atmospheric behavior from Earth's surface to altitudes exceeding 100,000 feet. The sky above us reveals itself not as empty space, but as a complex, structured, dynamic system whose properties change dramatically with height, while remaining interconnected across all altitudes. April 1st, 1960, Cape Canaveral, Florida. A Thor-able rocket streaks into the morning sky carrying humanity's first weather eye in space. TIROS-1 television infrared observation satellite weighs only 270 pounds and looks more like a hatbox than a revolutionary scientific instrument. But as it settles into orbit 150 miles above Earth's surface, this modest spacecraft prepares to transform our understanding of weather systems forever. 24 hours after launch, TIROS-1 transmits its first images back to Earth. The black and white photographs reveal something that no human has ever seen before: entire weather systems photographed from space. Massive spiral storms stretch across woe. Hundreds of miles of ocean. Cloud bands extend in organized patterns from horizon to horizon. For the first time, meteorologists can see weather as it truly exists as planetary-scale phenomena, extending far beyond the limited perspective available from ground-based observations. But it's the satellite's third day in orbit that produces the most dramatic discovery. TIROS-1 photographs a massive spiral storm system in the Atlantic Ocean, 800 miles wide, with a clearly defined eye at its center. Hurricane Betsy, still days away from threatening any land areas, appears in satellite imagery as a perfectly organized rotating system with winds exceeding 140 miles per hour. Here's what makes this image revolutionary. For the first time, meteorologists can see a hurricane's complete structure while it's still far from land. Ground-based observations only detect storms when they approach coastlines or when ships encounter them at sea. But satellite imagery reveals that hurricanes are much larger, more organized, and more long-lived than anyone previously imagined. The satellite perspective shows that Hurricane Betsy extends across an area larger than most American states. Its spiral bands of clouds follow precise mathematical curves as they wrap around the storm's center. The eye wall, a ring of the most intense thunderstorms surrounding the calm eye, appears as a perfect circle 30 miles in diameter. From space, the hurricane resembles a massive atmospheric engine, with clearly defined intake and exhaust patterns that organize the storm's circulation. TIROS-1's hurricane imagery establishes satellite meteorology as an essential tool for weather prediction and storm tracking. Within 5 years, a network of weather satellites provides continuous coverage of Earth's entire atmosphere, transmitting images every 30 minutes that reveal how weather systems develop, move, and interact across global scales. But satellites capture more than just visible images. Infrared sensors measure the temperature of cloud tops, revealing storm intensity and structure that's invisible to the naked eye. The coldest cloud tops, those reaching altitudes exceeding 50,000 feet, appear brightest in infrared imagery, indicating the most severe thunderstorms with the strongest updrafts. Satellite meteorologists learn to identify dangerous storms by their infrared signatures hours before they produce severe weather at ground level. Simultaneously, ground-based technology undergoes its own revolution with the development of Doppler radar systems that can measure wind speeds inside storms with unprecedented precision. Traditional radar only detects the presence and intensity of precipitation. Doppler radar adds a crucial capability. It measures how fast raindrops and ice crystals are moving toward or away from the radar antenna, revealing wind patterns within storms. The first Doppler weather radar installation begins operation in Norman, Oklahoma, in 1973, in the heart of America's Tornado Alley. Almost immediately, researchers make discoveries that revolutionize tornado forecasting and storm structure analysis. Doppler radar reveals that tornado formation follows a predictable sequence of events that occurs over 30 to 60 minutes before a tornado touches down. The process begins with the development of rotation in the middle levels of a thunderstorm, typically between 10 and 20,000 feet above ground level. This rotation, called a mesocyclone, appears on Doppler radar as a tight circulation pattern 10 to 15 miles in diameter. As the mesocyclone strengthens, rotation extends both upward and downward within the storm. When rotation reaches near the ground level, Doppler radar detects what meteorologists call a tornado vortex signature, a tight couplet of winds moving in opposite directions that indicates intense rotation in a very small area. This signature often appears on radar 15 to 30 minutes before a tornado becomes visible at ground level. Here's what Doppler measurements reveal about tornado wind speeds. The most intense tornadoes contain wind velocities that exceed anything previously measured in Earth's atmosphere. On May 3, 1999, Doppler radar near Moore, Oklahoma, measures wind speeds of 318 miles per hour in a tornado, the fastest winds ever recorded on our planet's surface. To put those wind speeds in perspective, they exceed the maximum sustained winds found in the strongest hurricanes by more than 100 miles per hour. At 318 miles per hour, wind forces become so extreme that they can lift automobiles, destroy reinforced concrete structures, and strip bark from trees. The pressure difference across a tornado vortex becomes so intense that buildings literally explode outward as the tornado passes overhead. But Doppler radar reveals something even more remarkable about severe thunderstorms. They have internal structure as complex and organized as the external spiral patterns visible in satellite imagery. Supercell thunderstorms, the type that produce the strongest tornadoes, contain rotating updrafts that extend from near ground level to altitudes exceeding 60,000 feet. These updrafts transport air upward at speeds exceeding 100 miles per hour, creating some of the most violent atmospheric circulation on Earth. The marriage of satellite imagery and Doppler radar capabilities leads to a new generation of storm researchers who pursue severe weather with unprecedented technological sophistication. Modern storm chasers deploy mobile radar units, atmospheric profiling systems, and real-time data transmission equipment that allows them to position scientific instruments directly in tornado paths. These mobile laboratories measure atmospheric conditions inside severe thunderstorms that would be impossible to study from safe distances. Researchers document pressure drops of more than 100 millibars, equivalent to climbing from sea level to 10,000 feet altitude within tornado cores in less than 30 seconds. They measure temperature differences of 40 degrees Fahrenheit between tornado centers and surrounding air, creating thermal gradients that add energy to the rotating circulation. But perhaps the most significant breakthrough in modern meteorology comes from the development of computer models capable of processing the enormous quantities of data collected by satellites, radar networks, and surface observation stations. Numerical weather prediction represents the ultimate fusion of atmospheric science, mathematics, and computational technology. Modern weather prediction models solve mathematical equations that describe atmospheric motion with extraordinary precision. These equations, based on fundamental physics principles like conservation of energy and momentum, calculate how temperature, pressure, humidity, and wind patterns change over time at millions of points throughout the atmosphere. The Global Forecast System, operated by the National Weather Service, processes data from more than 100,000 observation points around the world every 6 hours. This includes measurements from weather balloons released simultaneously from 800 locations worldwide, data from commercial aircraft flying predetermined routes, and continuous observations from geostationary weather satellites positioned 22,000 miles above the equator. Here's what makes modern weather prediction so computationally intensive. The atmosphere is a chaotic system where tiny changes in initial conditions can produce dramatically different outcomes. To account for this uncertainty, meteorologists run multiple versions of the same forecast model with slightly different starting conditions, creating ensemble forecasts that estimate the probability of various weather outcomes. Each model run requires solving millions of equations simultaneously, calculating atmospheric conditions at grid points spaced approximately 8 miles apart horizontally and every few hundred feet vertically throughout the entire global atmosphere. The most sophisticated models extend predictions 15 days into the future, requiring computational resources equivalent to millions of desktop computers working continuously. These computational advances extend weather prediction accuracy from the 3-day forecasts achievable in the 1970s to reliable 7-day predictions today. Hurricane track forecasts have improved so dramatically that current 5-day predictions are more accurate than 24-hour forecasts were 30 years ago. This improvement saves thousands of lives annually by providing earlier warning for evacuations and emergency preparations. But computer models reveal something profound about atmospheric behavior. Weather systems are interconnected across vast distances and timescales. A storm developing over the Pacific Ocean affects weather patterns in North America a week later. Drought conditions in one continent influence precipitation patterns on another continent months afterward. The atmosphere operates as a single, integrated system where local weather events reflect global-scale circulation patterns. Scientists discover atmospheric rivers, narrow bands of water vapor transport that carry moisture equivalent to 15 times the flow of the Mississippi River from tropical oceans to distant continents. These atmospheric conveyor belts, typically 1,000 miles long and only a few hundred miles wide, transport more water vapor than all the world's rivers combined. When atmospheric rivers encounter mountain ranges, they produce extreme precipitation events that can deliver several feet of snow or rain in 24 hours. The satellite and radar perspective also reveals that Earth's weather patterns follow predictable cycles and oscillations that occur over multiple years or decades. The El Niño Southern Oscillation affects global weather patterns every 2 to 7 years, as changes in Pacific Ocean temperatures alter atmospheric circulation patterns worldwide. When Pacific waters warm by just 3 degrees Celsius near the equator, the resulting changes create droughts in Australia, flooding in California, and altered storm tracks across North America. These discoveries demonstrate that weather prediction isn't just about forecasting tomorrow's conditions. It's about understanding how Earth's entire climate system responds to changing energy inputs and circulation patterns. Satellites provide the global perspective necessary to see these large-scale patterns, while Doppler radar reveals the small-scale processes that create individual storms and severe weather events. From Tyros 1's first hurricane images to modern supercomputer forecasts, This technological revolution transforms weather from an unpredictable force of nature into a comprehensible physical system governed by discoverable principles. The atmosphere reveals itself as a massive, complex machine whose operation can be observed, measured, and increasingly predicted with remarkable accuracy. Every weather forecast you see today builds upon the foundation established by satellite meteorology, Doppler radar measurements, and numerical weather prediction. The sky above us has surrendered many of its secrets to these technological tools, but continues to challenge our understanding with its incredible complexity and global interconnectedness. 2 miles beneath the surface of Antarctica, a drill bit bites into ice that fell as snow 800,000 years ago. The year is 1993, and an international team of scientists works around the clock at Vostok Station, one of the most remote research outposts on Earth. The temperature outside hovers at -80 degrees Fahrenheit, and the nearest civilization lies over 1,000 miles away. But what these researchers are extracting from the ice represents one of the most important climate records ever discovered, a detailed history of Earth's atmosphere stretching back nearly 1 million years. Each layer of ice in this Antarctic core contains tiny air bubbles that preserve samples of ancient atmosphere, like bottles of prehistoric air sealed away for millennia. As snow accumulated year after year, century after century, it compressed into ice while trapping the exact atmospheric composition that existed when each layer formed. The deeper the scientists drill, the further back in time they travel. Here's what makes these ice cores so extraordinary. They provide a direct measurement of atmospheric carbon dioxide levels throughout Earth's climate history. Advanced analytical techniques can extract air bubbles smaller than pinheads and determine the precise concentration of greenhouse gases they contain. The results paint a picture of atmospheric change that spans geological timescales. For 800,000 years, atmospheric carbon dioxide concentrations fluctuated between 180 and 300 parts per million, rising and falling in cycles that correspond to ice ages and interglacial periods. During the coldest glacial periods, when ice sheets covered much of North America and Europe, carbon dioxide levels dropped to their lowest points. During warm interglacial periods like the current epoch, they rose to their highest natural levels. But the ice core data reveals something unprecedented in this long climate record. Current atmospheric carbon dioxide concentrations exceed 420 parts per million, higher than any level recorded in the past 800,000 years. The rate of increase over the past century far exceeds any natural change documented in the ice core record, rising at speeds that typically take millennia to achieve. Naturally, the implications stagger the scientific community. Human activities have altered Earth's atmospheric composition more dramatically and rapidly than any natural process in the past million years. We're conducting an uncontrolled experiment with our planet's climate system, using atmospheric conditions that haven't existed since long before human civilization developed. To understand what these changing atmospheric conditions mean for future climate, scientists develop increasingly sophisticated computer models that simulate Earth's entire climate system. These models represent the culmination of centuries of atmospheric research, combining everything we've learned about weather, ocean circulation, ice dynamics, and atmospheric chemistry into comprehensive simulations of planetary climate. Global climate models divide Earth's surface into grid squares, approximately 50 miles on each side, extending from the ocean floor to the top of the atmosphere. Each grid square contains mathematical equations that describe how energy moves through the atmosphere, how water evaporates and condenses, how ice forms and melts, and how all these processes interact to create climate patterns. The computational requirements are staggering. Modern climate models process quintillions of calculations per second, mathematical operations equivalent to every person on Earth performing 1 million calculations per second simultaneously. These models simulate decades or centuries of climate evolution in computer runs that require months of continuous operation on the world's most powerful supercomputers. Here's what global climate models reveal about greenhouse gas effects. Carbon dioxide and other greenhouse gases act like an atmospheric blanket that traps heat radiating from Earth's surface. As these gas concentrations increase, they trap additional energy equivalent to detonating 400,000 Hiroshima bombs every day throughout Earth's atmosphere. This extra energy doesn't disappear. It accumulates in the climate system, raising temperatures, altering precipitation patterns, and changing atmospheric circulation. The warming effects aren't distributed evenly across the planet. Arctic regions experience temperature increases twice the global average, a phenomenon called polar amplification. As Arctic ice melts, it exposes darker ocean and land surfaces that absorb more solar radiation than reflective ice, creating a feedback loop that accelerates warming in polar regions. Weather stations from Svalbard in the Arctic Ocean to McMurdo Station in Antarctica document these dramatic changes. Arctic temperatures have increased by more than 4 degrees Fahrenheit since 1950, while Antarctic peninsula temperatures have risen even more dramatically. The Greenland ice sheet loses approximately 250 billion tons of ice annually, while Antarctic ice loss approaches 150 billion tons per year. These ice mass losses contribute to global sea level rise at rates exceeding 1/8 of an inch per year, a pace that seems modest until you consider the enormous volumes of water involved. The total ice loss from Greenland and Antarctica combined would fill Lake Superior, the largest of the Great Lakes, completely full every 4 years. But climate change affects more than just temperature and ice. Weather station networks around the world document shifts in precipitation patterns, storm intensities, and seasonal timing that reflect the changing energy balance in Earth's atmosphere. The jet stream, which controls much of the weather in temperate latitudes, shows increasing tendency toward persistent wave patterns that can lock weather systems in place for weeks at a time. These persistent atmospheric patterns create unprecedented weather extremes. Heat waves last longer and reach higher temperatures than historical records show. Drought conditions persist for multiple years in some regions, while other areas experience flooding events that exceed anything in local historical memory. The atmosphere, energized by additional greenhouse heating, produces more extreme weather events across multiple categories simultaneously. Scientists studying El Niño and La Niña cycles discover that these natural climate oscillations are intensifying as the overall climate system warms. Pacific Ocean temperature changes that drive these cycles now produce more dramatic effects on global weather patterns, creating stronger droughts, more intense floods, and more persistent atmospheric blocking patterns. The research reveals something profound about Earth's climate system. It's not simply a gradually changing average of weather conditions, but a complex system with thresholds, feedback loops, and tipping points that can produce rapid transitions between different climate states. Ice sheet collapse, forest die-offs, and ocean circulation changes can occur much faster than the gradual warming that triggers them. Ocean measurements reveal that the seas absorb approximately 90% of the excess heat trapped by greenhouse gases, buffering atmospheric temperature increases, but creating new challenges for marine ecosystems. Ocean temperatures in the top 2,000 feet of water have increased measurably throughout all ocean basins, affecting everything from coral reef survival to fish migration patterns. The oceans also absorb about 1/4 of all carbon dioxide emissions, preventing even more dramatic atmospheric increases, but making seawater increasingly acidic. Ocean pH has decreased by 0.1 units since the beginning of the industrial era, a change that seems small but represents a 30% increase in acidity. This ocean acidification affects marine organisms that build shells and skeletons from calcium carbonate, potentially disrupting entire ocean food webs. Satellite measurements provide a global perspective on climate change effects that would be impossible to document from ground-based observations alone. Sensors that measure Earth's energy balance show that the planet currently retains approximately 0.7 watts per square meter, more energy than it radiates back to space, a seemingly small imbalance that accumulates into enormous quantities of excess heat over global scales. Space-based observations also reveal changes in atmospheric circulation patterns that alter regional climate conditions worldwide. The Hadley circulation cells that control tropical precipitation patterns are expanding poleward, shifting desert boundaries, and affecting rainfall in subtropical regions. The Antarctic ozone hole, while beginning to recover due to international agreements restricting ozone-depleting chemicals, continues to influence southern hemisphere atmospheric circulation patterns. These global-scale changes demonstrate that climate operates as an integrated Earth system, where atmosphere, oceans, ice sheets, and land surfaces interact through complex feedback mechanisms. Changes in one component of the system propagate throughout all other components, creating cascading effects that can amplify or dampen the original disturbance. Climate scientists discover that the pace of change itself creates additional challenges for both natural and human systems. Species migration patterns, agricultural growing seasons, and water resource availability all must adapt to climate conditions that are changing faster than many natural adaptation processes can accommodate. The paleoclimate record from ice cores, ocean sediments, and other geological evidence shows that Earth's climate has experienced dramatic changes throughout geological history. But the current rate of change far exceeds anything documented in the geological record during periods when complex ecosystems and human civilizations could have survived. This perspective transforms climate change from an abstract future concern into an ongoing alteration of Earth's fundamental life support systems. The atmospheric composition that supported the development of agriculture, the growth of civilizations, and the evolution of current ecosystems is shifting toward conditions that haven't existed for millions of years. Understanding these changes requires integrating knowledge from every aspect of atmospheric science developed over the past several centuries. From Torricelli's first pressure measurements to satellite observations of global energy balance, each breakthrough in weather and climate science contributes to our comprehension of how Earth's climate system responds to changing atmospheric composition. The ice cores extracted from Antarctica's depths tell a story that connects directly to the satellite data streaming down from space, the computer models processing quintillions of calculations, and the weather instruments recording daily changes around the world. Climate science reveals itself as the ultimate synthesis of atmospheric understanding, requiring everything we've learned about pressure, temperature, circulation, and energy to comprehend how our planet's climate system operates and responds to change. Every breath we take now occurs within an atmosphere whose composition reflects both the natural processes that created our climate system and the human activities that are rapidly altering it. The hidden patterns in Earth's climate reveal themselves through ice preserved in Antarctica, energy measured from space, and mathematical models that simulate the entire planet's atmospheric behavior. In a laboratory at IBM Research, a quantum computer operates at temperatures colder than deep space, preparing to revolutionize weather prediction in ways that would seem like magic to earlier generations of meteorologists. This machine doesn't process information using the binary ones and zeros of conventional computers. Instead, it harnesses the strange properties of quantum mechanics, where particles exist in multiple states simultaneously until the moment they're observed. Quantum bits called qubits can perform millions of calculations in parallel, solving complex atmospheric equations at speeds that classical computers could never achieve. Here's what makes quantum computing so promising for weather prediction. The atmosphere is a chaotic system where tiny changes amplify into large-scale effects over time. Current weather models can provide reliable forecasts about 7 days into the future, but beyond that limit, prediction accuracy decreases rapidly due to the exponential growth of small uncertainties. Quantum computers promise to extend that forecasting horizon by solving atmospheric equations with unprecedented precision. A quantum weather model could process every molecule of air in a cubic mile of atmosphere, tracking individual particle interactions that current models must approximate using statistical methods. This molecular-level simulation might reveal weather prediction possibilities that seem impossible today. Accurate 15-day forecasts, precise precipitation timing down to the hour, and storm intensity predictions with error margins smaller than current measurement uncertainties. But quantum computing represents just one frontier in the technological revolution transforming atmospheric science. Artificial intelligence algorithms already analyze satellite data faster and more accurately than human meteorologists, identifying hurricane formation patterns 48 hours before traditional methods detect them. Machine learning systems trained on decades of weather data discover subtle atmospheric signatures that precede severe weather events. These AI algorithms can identify tornado formation probability from satellite imagery alone, detecting cloud patterns too complex for human observers to recognize consciously. They analyze millions of atmospheric variables simultaneously, finding correlations between seemingly unrelated measurements that reveal new insights about storm development. Artificial intelligence excels at pattern recognition in ways that complement traditional physics-based weather models. While conventional models solve mathematical equations describing atmospheric motion, AI systems learn directly from observed weather patterns, identifying statistical relationships that might not be obvious from physical principles alone. The combination of physics-based modeling and machine learning creates hybrid prediction systems more accurate than either approach alone. These technological advances support increasingly ambitious experiments in weather modification and atmospheric engineering. Scientists plan cloud seeding operations using charged particle beams delivered from aircraft flying above storm systems. Silver iodide cannons mounted on mountain peaks automatically fire precipitation-enhancing chemicals into passing clouds when atmospheric conditions favor snowfall enhancement. Space-based solar power satellites could beam microwave energy through the atmosphere to create controlled temperature gradients that influence local weather patterns. By heating specific atmospheric regions from orbit, future weather modification systems might strengthen or weaken developing storm systems, redirect hurricane paths, or enhance precipitation in drought-stricken areas. But these weather control technologies raise profound questions about unintended consequences and global atmospheric interconnections. Altering weather patterns in one region affects atmospheric circulation thousands of miles away. Increasing precipitation in one area might create drought conditions elsewhere. The jet stream patterns that control continental-scale weather could shift in response to localized weather modification, producing effects that cascade throughout the global climate system. The ultimate atmospheric mysteries continue to challenge our understanding, despite centuries of scientific progress. Consciousness and weather patterns share intriguing connections that remain unexplained by conventional atmospheric science. Some researchers investigate whether human emotional states correlate with local atmospheric conditions, examining whether collective psychological phenomena influence cloud formation, precipitation patterns, or electromagnetic fields in the atmosphere. Lightning represents another frontier where physics and mystery intersect. While we understand the basic electrical processes that create lightning, many aspects of thunderstorm electrification remain unexplained. Why do some storms produce thousands of lightning strikes while seemingly identical storms produce none? How do thunderstorms generate X-rays and gamma rays during lightning formation? What creates the mysterious ball lightning that occasionally appears during severe thunderstorms? The aurora borealis and aurora australis, the northern and southern lights, result from solar wind particles interacting with Earth's magnetic field and upper atmosphere. But predicting exactly when and where auroral displays will occur remains challenging despite our understanding of the underlying physics. The complex interactions between solar activity, Earth's magnetosphere, and atmospheric chemistry create light displays that dance across polar skies in patterns that seem almost conscious in their fluid grace. Future atmospheric research will likely focus on these boundary regions where known physics meets unexplained phenomena. Advanced instruments capable of measuring electromagnetic fields, particle interactions, and atmospheric chemistry at unprecedented precision might reveal new aspects of atmospheric behavior that current technology cannot detect. The search for life on other planets drives development of increasingly sophisticated atmospheric analysis techniques. When we discover exoplanets with potentially habitable atmospheres, we'll need to interpret atmospheric compositions and weather patterns. On worlds completely unlike Earth, the atmospheric science developed through centuries of studying our own planet becomes the foundation for understanding weather systems throughout the universe. Mars offers the closest laboratory for comparative atmospheric science. The Martian atmosphere, thin and dominated by carbon dioxide, produces weather phenomena both familiar and alien. Dust storms on Mars can engulf the entire planet for months, driven by solar heating and atmospheric dynamics that create wind patterns unlike anything on Earth. Understanding Martian weather helps us appreciate the unique characteristics that make Earth's atmosphere so hospitable to life. Venus provides another atmospheric extreme, with surface pressures 90 times greater than Earth's and temperatures exceeding 800 degrees Fahrenheit. The Venusian atmosphere consists almost entirely of carbon dioxide, with clouds of sulfuric acid, creating a runaway greenhouse effect that offers sobering insights into atmospheric physics under extreme conditions. These planetary comparisons reveal that Earth's atmosphere represents a delicate balance of conditions that could easily shift toward very different states. The ice core evidence showing atmospheric composition changes over geological timescales, combined with our growing understanding of planetary atmospheres throughout the solar system, emphasizes how remarkable our current atmospheric conditions truly are. Climate engineering proposals suggest increasingly dramatic interventions in Earth's atmospheric system. Solar radiation management schemes would inject reflective particles into the stratosphere to reduce incoming solar energy, essentially creating artificial volcanic cooling effects. Carbon dioxide removal technologies would extract greenhouse gases directly from the atmosphere, reversing some of the atmospheric composition changes documented in ice cores and atmospheric measurements. But these planetary-scale engineering projects require understanding atmospheric interactions at levels of sophistication that may be decades away. The atmosphere's chaotic nature means that large-scale interventions could produce unintended consequences that manifest years or decades after implementation. The interconnections between atmospheric chemistry, ocean circulation, ice dynamics, and ecosystem responses create feedback loops that are difficult to predict even with the most advanced climate models. The future of atmospheric science likely depends on international cooperation at unprecedented scales. Weather and climate systems operate globally, crossing all political boundaries and affecting every region of the planet. Understanding and potentially managing Earth's atmospheric future requires scientific collaboration, data sharing, and coordinated research efforts that transcend national interests. Satellite networks provide continuous global coverage of atmospheric conditions, but maintaining and expanding these systems requires international agreements and shared funding that reflects the global nature of atmospheric science. The most advanced climate models incorporate data from every continent and ocean, creating computational challenges that exceed the capabilities of any single institution or country. Perhaps most importantly, the future of atmospheric science involves questions that extend beyond prediction and control toward understanding our relationship with the air we breathe and the sky above our heads. Every breath connects us to atmospheric processes that span from molecular interactions to planetary-scale circulation patterns. The oxygen we depend on was created by photosynthetic organisms over billions of years. The nitrogen that comprises most of our atmosphere cycles through living systems, rock formations, and atmospheric chemistry in patterns that connect all life on Earth. Weather patterns influence human culture, agricultural practices, migration patterns, and settlement locations in ways that shaped the development of civilizations throughout history. Understanding how atmospheric changes might affect these deep connections between climate and human society becomes increasingly important as we alter atmospheric composition at rates unprecedented in human experience. The atmospheric science that began with ancient shamans reading cloud formations has evolved into a global enterprise that monitors Earth's entire climate system, using satellites, supercomputers, and international observation networks. But the fundamental human fascination with weather, the desire to understand the sky above us and predict what tomorrow might bring, remains unchanged. Future generations will inherit an atmosphere altered by our current activities, but they'll also inherit the accumulated knowledge of centuries of atmospheric research. From Torricelli's mercury barometer to quantum weather computers, from Franklin's lightning experiments to artificial intelligence storm prediction, each breakthrough builds upon previous discoveries while opening new frontiers of atmospheric understanding. The greatest mysteries may involve not just predicting weather and climate, but understanding how consciousness, life, and atmospheric processes interconnect in ways we're only beginning to appreciate. The air we breathe connects us not only to immediate weather conditions, but to the deep history of our planet, the evolution of life, and the cosmic processes that created the elements comprising our atmosphere. As we look toward tomorrow's atmosphere, we see both unprecedented challenges and extraordinary opportunities. The same technological capabilities that reveal concerning changes in Earth's climate system also provide tools for understanding and potentially addressing those changes. The international cooperation required for atmospheric monitoring and climate research demonstrates humanity's capacity for working together on planetary scale. Challenges. The atmosphere that surrounds us remains one of the most complex, beautiful, and essential systems on our planet. Every day brings new discoveries about how it works, how it's changing, and how it connects to every other aspect of Earth's habitability. The story of weather continues to unfold as an endless exploration into the fluid, dynamic, ever-changing ocean of air that makes all life possible. In the end, understanding our atmosphere means understanding our home. The weather we experience each day reflects processes and patterns that connect us to the deepest forces shaping our planet, from the solar energy driving all atmospheric motion to the quantum mechanical interactions determining how molecules absorb and emit radiation. Tomorrow's atmosphere will be shaped by the decisions we make today, but it will continue to surprise, challenge, and inspire us with its infinite complexity and essential role in making Earth the extraordinary world we call home.